Today we are going to discuss about the energy simulation procedure. Okay, so I think based on the strength, today we don't have streaming in the YouTube. Okay, so we will be having so I request everyone okay to join for this presentation through the Google Meet only. Okay. Okay, we will go to the presentation. So I will start my presentation. Okay. Yes, today we are going to discuss about the energy simulation procedure. Okay, so what is building energy simulation? Okay, so the introduction about the building energy simulation I have given through the heating load calculation. Okay, so now we are going into the simulation. Okay, building energy simulation. So what is the simulation? Okay, what is a simulation? Simulation is a problem analysis, okay, where we are finding the response of a predefined volume called as domain to the external excitation. Okay, so the predefined volume here, it is the building volume. Okay, it is not the air volume inside the building, it is the building volume. Okay, the external excitation includes ambient temperature, ambient humidity, climate, and internal heat gains and the HVAC systems. Okay, so these are all the external excitations to the building. Okay, so if I consider this part as the building, okay, so we are trying to find what is the response of the external excitation, what is the response of the external solar load, what is the infiltration load, okay, so outdoor air pressure. So what is the response on the system? Okay, system, by system we mean that building. Okay, and we know that the response depends on the material. Okay, we know that you consider the same building with a different material, the response will be different. For example, if I take a lightweight construction, so the temperature rise may be higher. Okay, but if I take a medium weight construction, so still the temperature rise will be reduced. So if I go for a heavyweight construction, okay, so we find that the temperature drop will be higher and there will be a shift in the peak. So that is what we have understood so far. So that means the response of the building, it is dependent on the material of the building. Okay, so it may be building material or it can be glazing material also. So what is glazing material? So we have variety of glazing materials. Okay, so you can have a plain glass or a tinted glass, or it can be a film, heat reflecting film. So it can be double paned glass. So the energy response of the building for different type of glasses will be different. Okay, so that is what we have to understand. So why I am stressing, because material properties are very important in the building energy simulation. So the response of the simulation, okay, to the input parameters, so it will vary with the material. Okay, so for different materials we will have a different response. So that is why in the building energy simulation we give special attention to materials. So we have a database of various materials inbuilt in the software. Okay, so mostly it is inbuilt in the software. So we have different varieties of construction material, different varieties of glazing material. So all these things will be there in inbuilt in the software. So we can just select the material and do the simulation. Okay, and simulation, it always need not be theoretical simulation, it can be experimental also. For this building, where air conditioning building, so you want to do the energy analysis, the same thing you can do it with instrumentation. So most of you may be aware of that. Okay, some of the building engineers, so they go with the instrumentation for measuring the energy. Okay, HVAC energy, lighting energy, and other energies entering into the building. So we can do it with the instrument. So if I am doing with the instrument, that is experimental. So the same thing, I can take the domain and you can integrate, and I can get some integral solutions. I can integrate and do that, but it will be very time consuming. Okay. So now we are going for numerical solution. So why we are going for numerical solutions? For buildings, okay, for buildings. So there will be a lot of components involved. And if you take a multi-storied buildings, we will be having different types of zones, different types of rooms, different types of floors. So inside that, we will be having different types of buildings, different shapes. So if you are going for analysis using integral method or experimental method, it will be very difficult for you. So if you are going for a numerical solution, it is very easy. Why? Because in a numerical solution, you will be dividing the domain into number of regular shaped subdomains. So each subdomain here we will be calling it as nodes. Okay. So in building simulation software, we will be using finite difference method, FDM method. Okay. So we will be drawing the building. Okay, so we will be modeling the building just like how we do it in finite element analysis and CFD. So we will be drawing the building, and after that, meshing will be automatically taking place. So we may not be able to see the meshing. Okay, it is one-dimensional meshing, so it will be automatically taking place. So after that, we will be running the simulation. Okay, to find what will be the temperature distribution throughout the building. Okay, all the building components. So after finding the temperature distribution, we'll be trying to find what is the energy content or energy entry into the building. Okay, so this is how we will be doing. Okay, so in the building simulation software, if I am going for numerical solution, the advantage is that I can solve for any building shape, number one, and any number of subzones like rooms or any number of floors can be included, and it can be solved simultaneously. And we can we can we can go for reduction in the cost. If you are going for experimental method, so you have to take lot of instruments and you have to enter into the building and you have to take lot of values. Okay, so and after that only you can calculate it. But if here you can sit in a room and you can model the building and you can find out what will be the energy consumption at various places. The process is theoretical, but we are going for numerical solution. Okay, so we are going for numerical solution. Okay, and also we should know that the CFD is also a numerical solution. So what is the difference between a CFD solution and energy simulation solution? In energy simulation solution, we will be solving only energy equation. Okay, thermal energy equation. But in a CFD solutions, we will be solving the flow equation such as continuity equation, momentum, and energy. Okay, so all the equations we will be solving. Okay, so that is the difference. So that is the difference between the CFD solutions and the numerical solutions. Okay, so what is the discretization? So I told that we are going to split the domain. Okay, first of all, we should understand what is our domain. So domain is a one-dimensional wall. Okay, so we know that if you cannot take all the walls together and then modeling, so it will be difficult. So in the building energy simulation, what we are doing is we are taking a wall. In that we will be having subcomponents. If I am taking a wall, for example, wall at the east, so it will be having some subcomponents. For example, it will be having a construction wall, and it may be having a glass, or it may be having door. Okay, wooden door. So that means a wall will be having different subcomponents. So what we are doing, we are dividing all these subcomponents, okay, into number of nodes. Like how we do it in FEA, how we are converting a domain into number of regular shaped subdomain called as meshes. There we call it as meshes. Even CFD also we call it as meshes. But here we are dividing it into number of nodes because it is one-dimensional and it is particularly by finite difference method. So we are dividing that into number of regular shaped subdomains. It is called as nodes. Okay, and our governing equation. So governing thermal energy equation. So we are going to see that. it is converted into number of algebraic equation for nodes. Because numerical solution, we will not be solving the equation directly. Okay, if I solve the equation directly, so it is called as integral solution. Uh, in a thermal governing energy equation, governing thermal energy equation, so the equations are converted into algebraic equations for the nodes. So since the equation is one dimensional, okay, so it is easy for us. Okay, so to easy for us to handle the solutions, it is easy for us to solve the solutions, and it is easy for us to handle the calculations. Okay, so how we are solving? So we are not going for three-dimensional solving. So we are going for one-dimensional solving. So each wall, okay, and its subcomponents such as glass and doors and the construction. So it is converted into a one-dimensional problem. Like it is divided into number of nodes. Okay, and for each node, we are converting the governing differential equation into algebraic equation, and we are solving for those algebraic series of algebraic equations, and we are getting the solutions. First of all, we have to understand that for a one-dimensional problem, the domain is a straight line. Okay, so even if it is look like a wall, okay, you should understand the area of cross section is constant. So though it is big, the area of the cross section, it will be constant. So it can be considered as a line with a constant area of cross section. Okay, and we will be giving the boundary conditions at the end points. So I have a line and I am giving boundary conditions at the end points. Okay, so at the end points, that means at the outer side, at the point we are giving the boundary condition. So you may be wondering, so you will be having a surface over which we will be giving the boundary condition. For example, solar boundary condition, temperature boundary condition, humidity boundary condition. But I'm saying that it is like a straight line. Okay, so consider that area, it is constant. Okay, the surface area, it is constant throughout the domain. So what happens? If areas becomes constant, you can just consider it as a line. So what you are doing is you are dividing the line into number of nodes. Okay, from inside to outside. So for each node, I am converting the governing equation into algebraic equation, and all those algebraic equations I am solving simultaneously using computer, because computer is very good in solving the simultaneous equations. Okay, simultaneous equations in the form of matrix. Okay, so now what is happening? The algebraic equations are there for zonal nodes. Zonal nodes are for each floor you will be having algebraic equations, and if I am combining all the floors, I'll be getting a very big matrix. Okay, so that means all are interlinked algebraic equations, and it will be solved simultaneously. Okay, so for each node, after solving the energy equation, so what I will be getting? Because in an energy equation, the variable is temperature. Okay, for all the nodes, I'll be getting the temperature. But that is what we are interested. If you are going for building energy simulation, so that is what we are interested. We are interested in the getting the energy. Okay, so with using the temperature, we can find out the energy at various grid points or nodes. So from that, you can calculate what is the amount of heat entry into the building, or you can even calculate what is the heat loss from a building in a winter condition. So both are possible. Okay, so discretization is important. You have to understand this concept, then only you can understand the concept better. Okay, so mathematically speaking, so we have the governing differential equation and boundary condition. So what is the one-dimensional equation that we are going to solve? So the one-dimensional equation that we are going to solve is this one only. So you might know that it is a Fourier equation, one-dimensional transient Fourier equation. So it is rho Cp dou t by dou t is equal to k into dou square t by dou x square. Okay. So if it is steady state, dou t by dou t will be equal to 0. So then I will have k into dou square t by dou x square is equal to 0. But now we don't have steady state in a cooling load calculation. So that is what we have seen already. In a cooling load calculation, we don't have a steady state. Okay, so only transient. So that means this is our equation. Okay, so this equation it is called as parabolic equation. Okay, so it is transient one-dimensional equation, and it is parabolic in nature because we have elliptic, parabolic, and hyperbolic equations. So these are all a simple parabolic equation because it is a time marching equation. So we call it as a parabolic equation. Okay, so which will be first order in uh, time, first order in time. Okay, so for this type of parabolic time marching problems, we require initial condition for solving the equation for solving the temperature distribution in the next time. So that means we have to give the temperature distribution at t is equal to 0. Okay, how we can understand? So you think that this is a wall. Okay, it is a one-dimensional wall. So there are not of nodes, small dots you are able to see. So all these dots are nodes. Okay, and all these points. Okay, now all these points, you think that at t is equal to 0, the temperature is 30 degrees. Okay, the temperature is 30 degrees. Okay, so for the sake of understanding, we will say take as 30 degrees. Okay, and after that, what is happening after t is equal to 0? We are applying a boundary conditions on the left hand side. Think that some solar radiation is falling on the surface of the wall. Okay, so what is happening is we are calculating what is the temperature distribution after 5 seconds using this equation. Okay, so this equation can be discretized as this equation. Okay, so this equation can be discretized as this equation. So regarding discretization, we will have a separate discussion. Okay, now we are in the process of understanding about the solver. We are in the first step. We need not go here and there. Okay, so first we will try to understand so that in all these nodes we will be having algebraic equations. So when I give the temperature distribution at t is equal to 0, that means on all the nodes the temperature is 0. So based on that, if you are doing the calculation, we will find that after 5 seconds the temperature distribution like this, because we are exciting on this side with the external radiation. So that means what will happen here? The temperature will be rising. Okay, the temperature will be rising here. On the other side, you think that we are maintaining at a constant temperature, maybe at room temperature. Okay, so after 5 seconds, we are finding that the temperature is increasing on the left hand side. Okay, because of radiation. So now when I want to calculate the temperature distribution at the 10th second, I cannot use the value at t is equal to 0. I have to use the value at t is equal to 5 seconds, or the temperature distribution at t is equal to 5 seconds. So the temperature has increased at the left hand side in all the nodes. Okay, so now I will give this temperature distribution, and after that I will find what is this temperature distribution. Slowly we can see that temperature is rising on the left hand side. Okay, because of the radiation. Okay, and after that we are taking this as input. Okay, so that means for every time step I have to give the present time step temperature distribution as the input, and I have to get the next time step distribution as the output. For example, if at 10 if you want the temperature distribution at the 20th second, I should give the value at temperature distribution at t is equal to 10 seconds. So I give this as input, and after that I will be getting this as output. Similarly, if I want the temperature distribution at the 30th second, I will be giving this temperature at t is equal to 20 seconds as the input, and I will be getting the temperature at t is equal to 30 seconds as the output. Okay, so this is how I will be having the temperature distribution. Okay, so this is how I will be having the temperature. So on the left hand side, I will find that the temperature will be increasing. So on the left hand side, I will find that the temperature will be increasing. Okay, and the right hand side I am not finding the temperature. So this is how the pattern will be for a time marching problem. So this is how we will be having a distribution in the wall also. So for example, if a wall is you consider this is the length of the wall, so this is the domain. Now I am taking the domain as a straight line, where I am giving the boundary condition at this point and this point. Okay, so that is what I told in the previous discussion. So for a one-dimensional problem, the domain is a straight line. I am giving the boundary condition at this point and the inside point. Okay, and after that I am going for a time marching solution. So I am giving the temperature distribution at t is equal to 0, and after that I am calculating what is the temperature distribution in 5 seconds. So like that I march in time to find out what will be the temperature distribution. So in these types of problems, what are all the important parameters we should know? Time steps should be given and total time should be given. Okay, and we should know that when I am going for energy simulation, if I am going for energy simulation per day, my temperature total time will be 24 hours. 24 hours into 60 into 60 seconds. Okay, and I can choose my own time steps. Okay, So here in most of the solvers, okay, so it takes 1 hour. Okay, so I've seen that most of the energy solvers are heat cooling design calculation solvers. It takes 1 hour as the uh, 1 hour as the time step, and they will be solving 24 steps. Okay, and the same thing can be done for every minute also. It is possible that you can have the time steps as 1 minute, and the total time then it will become 24 into 60. Okay, so that will be the total time. So that means for each time step I have to give 60, I mean 1 minute. Okay, so 1 minute as the time step. Okay, so the total number of minutes will be 24 into 60 minutes. Okay, so similarly if I can do that by 1 second also, if I am doing it for 1 second, so the total number of seconds will be 24 into 60 into 60, and my time step will be 1 second. Okay, so when I do it for 1 second, when I do it for 1 second, so I'll be having maximum accuracy, because last class we had a discussion, even now also we will be having the same discussion. So we have found that if the time step is more, the accuracy is less. Okay, when you go for time integration. So if I go for a lesser time step, I'll be getting the best possible solution. For that also I have given the example in the last class. Okay, so the solution at the previous time step will become the initial condition for the next time step. This we should not forget at all. Okay, so that is the basis. Okay, so if possible, I think we will have a numerical simple. We will solve a simple numerical problem for having a better understanding of this energy simulation software. So my governing differential equation is one-dimensional Fourier equation, transient one-dimensional Fourier equation. Okay, so when I discretize, it will be in this form. Okay, so this will be I. So this is ij. So this will be p plus 1 tp. Okay, so we will be this is only one direction. So even this j, it need not be there. Okay, so it is a t of I plus 1 plus t of I minus 1 minus 2 tp. So you might be wondering, what is this? So if this is in the algebraic, I mean exact form, or differential form, for this algebraic equivalent of dou square t by dou x square, it is given by this. So it is usually brought from the Taylor series. So when we go for CFD, we will discuss about this also. Okay, so I will take a session for this also, how we are discretizing. Okay, and after that, okay, so how my building energy simulation software will be. Okay, so I told it is a one-dimensional problem. So that means a one-dimensional parabolic problem. So that means for every direction I am going to have these models. Suppose I am taking a east wall. So east wall, I will be having a 1D model, wall model. Wall model means it is for construction, brick construction. Okay, so it may be a heavy weight, medium weight, or lightweight construction. So for that we are introducing nodes and we are trying to solve the problem. Okay, and even for door also we have to introduce the nodes and we have to solve the problem. Similarly for window, okay, window glass. So there also we have to introduce nodes. So some of you will be wondering, window only radiation will be entering into the building. So why I have to introduce nodes in the windows or glass? So we may be knowing, so glass will be transmitting the radiation. Okay, transmitting the radiation, short wave radiation, directly into the room. Okay, so we are not worried about that. So we are worried about the absorption component. Okay, so the total heat entering into the building, two components will be there. One is transmitted component, the other one will be the uh, absorption component. So this absorption component, so uh, it will be by the process of conduction. Okay, so for that we are generating, okay, we are generating the nodes and we are trying to capture the temperature distribution in the glass. Okay, so and that is how for glass also, even for door also, we can go for FDM solutions. Okay, so what is that it is going to happen? So my model is one-dimensional model. So I just shown for east. So when I am going for a building simulation software, so there I cannot say like a load calculation east, west, north, south, and all. Okay, because it is not any building. It is not going to be perfectly east, west, north, south. There will be small amount of deviation will be there. Occasionally or very rarely it may be coinciding. Okay, so in that case, that means what I have to do. So in building simulation software, I should not call it as east west north south or northeast northwest southeast southwest. So I should call it as direction 1, direction 2, direction 3, direction 4. Okay. So I have to just mention the what is the orientation with respect to north or with respect to south. So if I am able to mention the orientation, so automatically 4 directions will come. So you need not interpolate between east and southeast, okay, or west and southwest. So you need not go like that. So each depending on the degree orientation, okay, 360-degree orientation. So you can give for each wall. So that means hereafter you can drop that east, west, north, south, and roof for building. Okay, so it will be designated as direction 1, direction 2, direction 3, direction 4, direction 5. Okay, and we are going to give the orientation, okay, with respect to south or with respect to north, depending on the type of software. Okay, and so that means for each direction I am going to have the model. Okay, so for east, west, north, south, and roof, and even for floor also. Okay, so I'll be having a model. So that means what will be the input? This input for these models will be radiation, ambient temperature, and the properties. Okay, now you can take this is the radiation model. Okay, so this is the radiation input model. So already I told you when I was discussing the topic 1. Okay, so I told that these radiation models are very important because they form the input for building energy simulation software. Okay, so how they form the input for the building energy software? Okay, so you know that when the radiations, when it is falling on the surface of the ball, okay, so it will have 2 components, beam radiation and diffuse radiation. Beam radiations are short radiations which are falling directly on the wall. Okay, and the diffuse radiations are long radiations, that means it will have less intensity or less temperature compared to beam radiation, and it will be in the diffused form. How the radiation will become diffused? Radiation, when it is falling on the surface of the earth, so before falling on the surface of the building, so it may be falling on clouds or surrounding walls, surrounding water body. So because of that, it will undergo multiple reflection. Because of multiple reflections, so this the short radiation, beam radiation, will be converted into diffuse radiation. Okay, because of multiple reflection. Okay, so that means whenever you have a building or a door or a glass, so radiations will be falling on the surface. So it will have 2 components, beam radiation and diffuse radiation. So diffuse radiation is directionless. That means if you have the area of the wall or if you have the area of the glass, so full area it will be available. But the beam radiation, it is highly coherent and it will be falling on separate specific area only. For example, if you have a glass, clear glass, so in the morning you will find that, suppose if you have a overhang over the window, in the morning you will find that only 1/4 of the window the radiation will be entering into. So radiation means visible light. Short beam radiation means it is visible light, directly it will be entering into the building, it will be falling on the floor. So that means when you are accounting for beam radiation, so you have to take, because of the overhang which will be blocking the direct radiation, so only 1/4 of the window will be visible. So that is beam radiation. Okay, so that means for beam radiation, the area you will be taking only that much area, but for diffuse radiation we will be taking the full area, because that will be available for the full window. So that is how these two we have to differentiate ourselves. Okay, fine. How you are going to get this value of beam radiation and diffuse radiation? Okay, so we will be having a radiation models. So in all the radiation models we will have, so we have an Ashrae model. Okay, so and we have other models also. So in all these things we will be giving the latitude and the latitude location as the input for the radiation model. Okay, so you may be knowing what is why we are giving a latitude location, okay, for the radiation model, because with the latitude our climate is changing, radiation amount of radiation received is changing. Class 1 we have discussed. Okay, and also longitude also important. So why longitude is important? Because from the morning till the evening, okay, so my radiation is changing. So it is changing with the longitude. So we call it as hour angle. Okay, we call it as hour angle. So hour angle, it is almost similar to longitude lines. Okay, so we can divide that into divide the globe, okay, into 24 hours. Okay, so you divide 360 by 24 hours. Okay, so you'll be getting 15 degrees. Okay, so that means for every 15 degrees, you'll be having 1 hour. Okay, so why I have to take that as input? Because you know that for every 1 hour, the radiation will be changing. During night time, you will not be having radiation. So during the daytime, you will be having the day length. Depending on the latitude, you will be having the day length, and you may be having a very big day length or a shorter day length. That also depends on the latitude. And after knowing the day length, the radiation will be varying in the day length for every hour. So that will be given in the form of hour angle. So that is what I call it as the longitude angle. Okay, longitude angle. So latitude angle is also important, longitude angle is also important. Okay, so that we give it as the input to the radiation model. So that means there will be some algebraic expressions. We will be giving these angles. So automatically it will be generating what will be the amount of radiation. Okay, and for if I am doing it for the full year, okay, so that means I can do it. I have to change the declination angle. Okay, because every day we are getting a radiation. How this becomes different? Okay, so we can think from the December equinox. Okay, the sun will be at the tropic of Capricorn, so that is minus 23.5 degree south latitude. So from there it will go to up to June equinox. Okay, I'm sorry, it is a June solstice. I'm very sorry. Okay, from December solstice. Okay, the sun will be at the tropic of Capricorn. So from the tropic of Capricorn, it will be moving towards the northern hemisphere. So it will be reaching the extreme end of northern hemisphere, that is the tropic of Cancer, at June solstice. Okay, at the June solstice, the sun will be at the peak, and again it will be coming back from the northern hemisphere up to the month of December. Okay, so that means the sun is moving from minus 23.5 south latitude to the plus 23.5 north latitude. From 23.5 north latitude, it is coming down to 23.5 south latitude. So that means the latitude is changing. Okay, so throughout the year the latitude is changing. Okay, so at the December 22nd, so the latitude is minus 23.5. Okay, so at June, okay, 22nd, the latitude is plus 23.5. Okay, so in between it moves from the so you know on the way at 0. Okay, when it is moving from the December solstice towards June solstice, on the way it will undergo equinox. Okay, so on the way it will be having March equinox. Okay, similarly, that means at March equinox the sun will be at 0 degree, that is at the equator. Similarly, when it is coming from the June solstice, okay, towards the December solstice, so it will be crossing September equinox. Okay, so again it is at 0 degrees. So now you can clearly understand that the sun is making one movement towards north, and again it is coming back. So this movement you can give it in the form of angle. So that angle is called as declination angle. So the declination angle will be varying from minus 23.5 to plus 23.5. Again minus 20. It will come back to minus 23.5. Okay, so that is given by the declination angle. Okay, so so this is how we are in the radiation model. Okay, so we will be having expressions for radiation model. So we will be giving all these angles. By varying all these angles, so we will your beam radiation and the diffuse radiation will be varying throughout the year. Okay, so for every latitude we have latitude angle. Okay, and for any location. Okay, so for a location, so we have a latitude angle. So for every latitude, the sun movement is given by declination angle, and the hourly variation it is given by hour angle, or you can call it as longitude angle also, but the correct term is hour angle only. Okay, so using this you can have a input model, so that is the input radiation model, so that can be given. So this will be given to all the walls. Okay, so now hereafter in energy simulation we need not call it as east, west, north, south, roof. So you can tell direction 1, direction 2, direction 3, direction 4. Okay, and you can give the orientation also. Okay, so what this simulation will do, so it will give the input, so like what we have seen here. Okay, so it will give the input on the left side, and it will try to find out what will be the temperature distribution. So after finding the temperature distribution in the all the wards, so we will be having the room model. So the room model will be like coupling all these things. Okay, so whatever the heat coming from the temperature coming from east, temperature coming from west, temperature coming from north, south, roof, everything it will be linked to the room model. So using that, we will be trying to find out what will be the temperature inside the room. Okay, all these temperature informations will be useful for us for finding the wall heat flux, wall and roof temperature variation, room temperature variations. So you can calculate what is the energy entry into the building. Okay, so that is how we are going to have. And also we should know not only the radiation model, so we are going to have the ambient temperature also. Okay, so we are going to give the ambient temperature also as one of the parameter, because radiation directly falls on the surface of the wall, but on the other side we are having ambient temperature, and if that ambient temperature is low, then the radiation will move in this side. Okay, and if that ambient temperature is higher, so then the heat will move towards the building. Okay, so in an air conditioner building, always the heat will be moving towards the building, because the building will be maintained at a low temperature. But if it is a free running building, free running means inside you are not air conditioned. So what will happen? Both the things are possible. Heat may enter into the building. Sometimes heat may go out of the building also. So don't always think that since the solar radiation is falling inside the building, always heat will be moving into the building. So we have found with our simulations, some point of time the heat from inside the building moves out of the building. That is also possible. Okay, so this is how we will be doing the building energy simulation. And okay, so what are the components of the building energy simulation, or what are all the important components of the building energy simulation solvers? If I am going for a BSS, that is building simulation software, so there will be provision for giving the building location, that is latitude, geometry. We are going to draw the model of the building, and we are going to give the orientation also. Just now I told you what is the importance of orientation. Okay, always a building need not be perpendicular to east, west, north, south. Okay, so there will be orientation. So that orientation also we have to take into picture, and we have to have the windows and optical properties and the shading devices. So we should have a database of all the glazing properties. Okay, similarly weather information also we should have. So if there is a precipitation, okay, or if there is a moisture, regarding moisture, so all these informations we have to give it to the solver. Okay, so then only it will give a correct simulation. And wall construction material and its properties, thermal properties, mostly thermal properties only we will be giving, because we are doing a thermal energy simulation. Okay, and if at all you are linking the building simulation software with the plant model, so then you should have plant details. Okay, and the people, equipment, and other things. So already we have discussed about this. So that also, and the schedule of this people and equipment, that also you have to give. Okay, because we will be switching on the computer and switching on the lights in an office only for specific time. So that specific time it is called as a schedule. So that we have to give it. If you are doing load calculation, that is not required. But if you are going for energy simulation, it is very much required. So we are going to see that in today's discussion. Okay. Also, we have to have the details of lighting. Okay. And these are all the things what we are going to get outside. Already we have discussed what is the temperature, thermal comfort inside. So what is the peak cooling load for cooling load calculation, and detailed energy balance of the building components, breakdown of load contributors. You can find what is in the direction 1, direction 2, direction 3, direction 4, east, west, north, south. Okay, and annual energy requirements. So that also we can give it. Okay, annual energy requirements also. So that means what you have to carry out a year-round simulation. So whatever I told, it is told for a day. No, but there is no absolutely no problem in extending this. Okay, extending this to uh, 24 to 1 week, and you can extend it for 1 month. Okay, even you can do it for 1 year also. So that is possible. Okay, but for that you should all the data. Okay, so like if you want to simulate for 1 day, data pertaining to 1 day, input data pertaining to 1 day, it is sufficient. If you want to simulate for 1 week or 1 month, so input data pertaining to 1 month, you have to give it. Similarly, if you do it for, if you want to do it for 1 year, so then input data pertaining to 1 year, that is very much required. And this we have seen in the last discussions for load calculations. I told that we are calculating only for the peak. Okay, we are calculating only for the peak day, peak time in the peak day. But here you can see that we are having external excitation. Okay, so external excitation, it is for 24 hours. So that means just now I told, if you want to simulate for 24 hours, you require what is the ambient temperature for 24 hours, what is the specific humidity for 24 hours, what is the solar radiation, okay, for east, west, north, south, and roof, okay, for 24 hours. Okay, so but usually it will be only for 12 hours. So that details also I have to give it. And after that, I have to find what is the response of the building. What is the response of the building? So what will be the temperature rise inside the building? So you can see the temperature of the wall east. Okay, so you can find out what is the temperature of wall east. So wall east, here it is higher. Okay, so then it is decreasing. Then wall west, it is higher in this point. And here you can, for the building, what I have shown it, roof value is very much higher. So roof is not insulated. So that's why we are having very much higher. So that is what is controlling everything. Okay. So this I call it as the response of the system. Okay, so now you should understand what is external excitation. What is the domain? Domain is the wall, or it is a piece of glass, or sorry, window, a glass for the window, or it is the door. Okay, so that is the domain. So we are dividing that into number of nodes. So what is the response of the domain? The temperature distribution in the wall, glass, and everything. Okay, roof, everything. So that is what we are having here. And we have to give the humidity also. If you want to have load calculation, you have to give the humidity also. Okay, because in the load calculation, we have seen the difference between the indoor and the outdoor humidity that will going to contribute for the latent loads. So that if you have to give it, okay, latent loads we have to give it for load calculation. So that means you know, in a building a simulation software, so all these components will be there. We are going to see that. So whatever I shown, it is for a 24 hours. Okay, so and we have got the final distribution. Okay, so we have got the final distribution like this. So this is the heat load inside the building. Okay, for the 17th July. Okay, this is for 24 hours. So now you have understood how to simulate for 24 hours. So this program we have written. Okay, ourselves we have written, and so it has been written in MATLAB. Okay, so, and we have done this. And if I am okay, so the most important things, I want to have a discussion on this. Whatever we are getting, it is the rate of heat gain that we should understand. In the heat load, whatever the grand total heat we are calculating, or the tonnage, whatever you are calculating, so it is the rate of heat gain only. So whatever you call it, it is rate of heat gain only. So you can always convert that into joules per minute or joules per second. That is watts. So here it is 1120. It is a small model building which you have simulated. So it is 1120 watts. That is joules per second. If you want to find out what is the rate of heat gain per minute, so it is just you have to multiply that by 60. So then I will be getting what is the rate of heat gain per minute. Similarly, I can do that for the rate of heat gain per hour. Okay. So this is how you have to multiply. So while doing that, okay, so if you are doing this, what is that you are doing? If it is for a, if your calculation is for a second, so that means your calculation is continuous. Okay, your calculation is continuous. So if you are doing the calculation for every minute, that means you are doing only one calculation, and after that you are multiplying that for 60. Or you can all the quantities you can work it in terms of joules per minute. You can do the energy balance in terms of joules per minute and you can give it. Okay. Similarly, you can have whatever the value per second. Okay. So if you are calculating the radiation, so you can convert that into per hour basis, and you can perform the energy balance for per hour or energy simulation per hour. So that is how you are going to get what is the rate of heat gain per hour. But it is you compare per second with per minute, the amount of approximation is higher for per minute, and still it is higher for per hour. Why we have to understand? Because if I am calculating for per hour, throughout that hour we are considered that rate of heat gain is this much only, so it is constant throughout the hour. Okay. But if you are calculating at a rate of per minute, so it means that for every minute it is constant. So that means for the 60 minutes there will be 60 values will be there. Okay. But if you are calculating for with watts, so that means the values will be different. So that you will be having 3600 values. Okay. 3600 values for every seconds. So that means the plot is going to be like this. The plot is going to be continuous. For every hour it is going to be continuous. If I am going to do it for every hour, so then it is going to be discontinuous. So it is going to be like this. So already I shown you. It's going to be like this. It's a step for every hour. Okay. So when I am going to add that, okay, so the discussion is going to be approximate. So that means when you are doing the energy balance, okay, if you want more accuracy, you can reduce the time step. So here I am reducing the time step for every hour. I am calculating for every second. So the accuracy is more. So if I am doing it for every minute, okay, so the accuracy will be definitely lesser, because it will be, you will be having step for every minute. Similarly, for every hour you will be having step for every hour. So that means the accuracy will be very much lesser. So, and yeah, first and foremost you should understand, if you are an energy engineer, you should understand that the rate of heat entry, so all those are called as power. It will be in watts. Okay. If you want energy, so that means it is mathematically speaking it is integral of PdT. But simply speaking it is energy, it is rate of consumption into time. Okay. So that means watts into time. So that is what you are going to get energy. So if you want to calculate energy per minute, just multiply by the value multiplied by the seconds. So you are going to get that energy. So if, I think this, I think so many joules per minute. So the unit will be joules. So similarly, this will be so many joules per hour. Okay, so that becomes energy. Okay, so per day, energy consumed per day means what? So you multiply by all the values. Okay, so then you will be getting per day. So rate of energy consumption per multiply. So that is how it will go. So here you can see that is how we will go. So you are calculating for every 1 hour, so it will be like a rectangles. Okay. So if you are finding the area under this curve, okay, so then I am going to get what is the energy. So the area under this curve are integral of P dt, power into time. So everything it is going to give me the energy. Or simply it is very simple to understand. Okay, so value into, so into the time, corresponding time. Okay, so I am going to get the energy. If the step of time step is very much lesser, I am going to get it accurately. So that is what we know from numerical integration. If the time step is smaller, you get accurate values. Okay. So if the time step is larger, okay, so you will not get a accurate value. So here you can see for every 2 hours I am making the calculation. So it's not accurate. There is a deviation from the calculated value. Okay. And so that is why my conclusion is you do it for every second. So then you will be getting an accurate value. Okay. So that is possible. Now I think in standard solvers, okay, so they are giving it for every hour only. Okay. But we have made calculations. Okay, we have made energy simulation solver which can calculate for every second. Okay, so and that value can be taken. Okay, that value can be taken and you can convert it. You can always convert it for per minute or per hour basis. Okay, so the best will be with the lower time steps only. Okay, so that is what I want to convey. Okay. And this is related with the energy consumption. Please note that. Okay, it is related. If you want to calculate accurately, go for 1 second time step. You want to improve, or if you want to the next level will be 1 minute, then next level will be 1 hour. Okay, And beyond that, if you go, and it will be totally approximate. Okay, so it will not be very relevant result. Okay. Okay, so that is what we think. So then we are going to the uh, building model. Okay, so in the building model, so what is the hierarchy with which we will be having the model? In a building, if I go, so first I will be having the site. Site means you will be knowing. So that is a location where multiple buildings may be there. Okay, and in buildings you will be having several blocks, but we may not be calling it as block. We may be calling it as floors. First floor, second floor, third floor. Okay, so those types of floors only they are calling it as blocks. In the floors, okay, so you'll be having multiple zones. Zone means several rooms will be there. Okay, so for example, first floor means there will be lot of rooms will be there inside. Okay, so that is, those are all called as zones. So then from the zones, if I'm taking a room, what will be there in the room? So I'll be having four surfaces. Okay, maybe if you want to understand, it is like east, west, north, south, roof and floor. Four surfaces will be there. So that is what I call it as the surface. Okay, and if I take a surface, if I take east surface, what are will be there in a surface? So in a east surface, I'll be having the construction, the glass. Okay, construction material, glass, door. I'm telling for example. So all these things may be there. Okay, so this is how you will be having the hierarchy. Okay, so that means when you are just now I told you. So when I'm using a finite difference modeling, so that means I am doing it for the opening only. Okay, so these openings will be there on the surfaces. Okay, so that means for construction I'll be doing, for window I'll be doing, for door I'll be doing. Okay, so this will be cumulative. Okay, so for east I'll be calculating. Similarly, I'll be doing for west. Then north, south, roof, floor. I'll be adding everything. Okay, so then it will be adding to the zone. That means for that room. So if I am taking a room, there will be multiple rooms in a floor. For example, 10th floor means there may be 20 rooms. So all these things added together, it will be going toward the 10th floor. So that is called as a block. And in a building, so you may be having 20 floors. So all these 20 floors, you can club it together. That will be building. Okay, and if you are going for a software park, okay, so there will be one building. Okay, stage one will be in here, and the stage one will be after another 1 kilometer. Okay, so that is how in a site you can have multiple buildings. So this model hierarchy, it has been worked out very clearly. Okay, for us to understand. So uh, to make it easy for us to understand and work out calculations. Okay, and how this will be. So if I'm going to a solver, okay, so if I'm going to a solver, so I took it from a design builder solver. How this will be? Okay, so this is a building model. Okay, this is a building model, and this total thing, it is called as a building one. Okay, and this is a site, untitled here site. So that means in the site I can have building one and building two. So it may be appearing down, so it's not shown here. So that means what, this untitled is the site. Building one may be there. So that means one more building two will be there, building three will be there, building four will be there. So now I have taken one building. Okay, so take that I have taken one building like this. Okay, so this is the building what I have taken. So for that building, I have various zones. Okay, so this is zone one. Various blocks. That means various floors are there. So that means what? 1, 2, 3, 4. So here I have shown only 3 floors because for the sake of clarity. Okay, then only I can show it in the PPT. So that's why I've shown only 4 block. So here you can see this is block. That means 1 floor. So this 1 floor is there here. Okay, so like that you can take. So this is second floor. This is third floor. So one more floor is left out. It is there down. Okay, and in the floor. Okay, so I should have number of rooms. But unfortunately here it is only one room it is shown. Okay, because if I put more things, you cannot see. Okay, so that means please try to understand, if block 1 means it is for 1 floor, you think that it is a ground floor. Okay, if it is a ground floor, then you can have multiple rooms. So that means you can have multiple zones. But what is happening in this building is this full thing is like a big hall. So that means the ground floor is like a big hall with 4 walls and 1 ceiling. Okay, 4 walls and 1 ceiling. So that is what is given here. Okay, so similarly if I go for block 2, so that means the second floor. Okay, so again there you can see the zone is called as humidity control zone, and that is also like one big room. But in reality you may have multiple zones here. Similarly in multiple zones here. Okay, Similarly, block 3, that is the third floor, you will have multiple zones. Similarly, in fourth floor, you'll be having multiple zones. But unfortunately, we are having only one zone. So that means one room is there. One room is there with ground floor, ceiling, okay, wall, 4 walls. So similarly, here you can see I have 4 walls, floor, and the ceiling. Okay, so that is what is given here. Okay, so that is what is given here. Okay, so this is like this. This is the hierarchy. Now you are able to see the hierarchy. What I told here. Okay, site, building, multiple buildings. Similarly, in buildings you will have multiple floors. Similarly, in floors you will having multiple rooms, and from rooms you will be having multiple surfaces. Okay, and you will have in each surface you will have multiple openings. So now you can go step further. You can click this wall. What is there in the in ceiling? I'm clicking, so I'm having an element component. So in the wall, I have 2 components. One is external wall construction and window. Similarly, in each wall, see here you can see in this wall, I'm clicking. So I have external construction and 3 windows. So here you can see 1, 2, 3 windows are there. So that is what is shown here. So that means wall is also having 3 components. So these 3 components we called that as opening. Okay, we called that opening. So that means if you want to do that finite difference calculation, so it will start from here only. Okay, so here, so this only will be this external wall only you will be dividing that. Okay, similarly windows you will be dividing that. So that is how the computer also it will understand. Okay, so because it should be structured, then only it can understand. And fortunately, you are dealing with the building, so everything is in the Cartesian coordinates, and everything will be structured. So it is easy for you to understand. Okay, but it is not going to be the case if you are going for a different type of CFD analysis or a different type of numerical analysis. So now I am taking. Okay, so now that I am taking, so for each of these components, I am going to do the discretization, and I am going to do the I'm going to give the boundary conditions. I am going to give the simulations. So when I do that, okay, how the discretization will be. So mathematically, if I so this is like each components. Now whatever you have seen, these are all the each components. Here you can see he has divided. This is a line. I told no domain is like a line, and he has divided that line into number of nodes. So similarly here, so this is a boundary condition is given in the first node. Okay, so this is internal convection. That is air conditioned system is there inside. Okay. Similarly, adjacent zone radiation. Okay, so every component is there. Adjacent zone convection, construction node, transient. So if construction is there, in that transient simulation only will be taking place. So that I have to put it here. Okay, so that means even opaque surface. Opaque surface means again it is like a construction only, or it may be like a door. Okay, transparent surface. So internal generation. So this also it is converted directly. It is added to that node. Room. Inside the room also we are maintaining it like a node. So that will be helping us for making energy balance very easily. So that means what? All the building components I am converting into one-dimensional nodes. Okay, and so my zonal matrix. Okay, so my zonal matrix it is going to be like this. Regarding matrix and all, you will be finding it difficult at this point. You have to understand. Whoever knows about matrix, just try to understand that the full matrix for a building it will be like this. So and for construction 1, construction 2, construction 3, construction 4, that is like east, west, north, south, roof, like that it will go. So that means for every room you will be having a matrix like this. Every floor it will be a very big matrix. For full building it is going to be a huge matrix. Okay, and we should understand that the equations like this. Okay, so the equations whatever we have seen. So like this, it has been converted. Okay, so this equations like this, okay, it has been converted into algebraic equation using discretization, and that only it is converted into algebraic equation. But that algebraic equation also it is that also it should be transient. You should be knowing. So this is a transient algebraic equation. So that you can see it is in the form of a matrix. So if in FEA you will be calling it as a stiffness matrix. Okay, here we will be calling it as thermal matrix, because FEA it is you will be dealing with elastic materials, iron like other materials will be handling. Okay, but here you are going to these are all the building properties. Okay, building properties matrix. So for example, here the properties all rho Cp, thermal properties for wall that will be the rho Cp K, Mostly that properties will be arranged in a tridiagonal form. Okay, mostly one dimensionally it will be in a tridiagonal form. So all this tridiagonal matrix will be appearing here. Okay, and you can see it. You have the temperature vector here. What is that temperature vector? It is a n by 1. Okay, so it is a n by 1, or how many number of nodes totally, so many number of temperatures will be there. So that means for every time step, if a building, multi-storied building is there, it is possible that you can even have 10 lakh temperature nodes. So that means your matrix will be 10 lakh by 10 lakh. If it is a square matrix, mostly it may not be a square matrix. Okay, because of interconnectivity and all it is there. Okay, so that means a 10 lakh temperature distribution will be there. So that means what? You are giving the building matrix. Okay, so building matrix, and you have a B matrix. So I told you have to, if you want the temperature distribution, 10 lakh temperature distribution around the building, so that means you have to give the initial condition. Before that time step, what is the value you have calculated? That you have to give it as the input on the right hand side. So that is what I call it as transient. So if I give that 10 lakh time temperature distribution as a column matrix, so here I will be getting the 10 lakh temperature distribution in the next time step. Okay, so that is how I do the time marching. Okay, so what I have to do, just I have to find out what is theta n plus 1. So how you can do that? This you can take it to the other side, or if you want to solve a direct method. Okay, so this can go out on the other side. And if it is A, this will become A inverse on the other side. And you can directly solve and you can find out the temperature distribution. As the first step, you can know like this. Okay, as a first step, you can know like this. So that means what is that you have to understand? You are trying to find out what you are dividing the building subcomponents into number of nodes, and you are trying to find out the temperature distribution by giving the boundary conditions at the various nodes. So even in this matrix also, your boundary conditions will be in C. All your external excitation, that is the radiation, ambient temperature, precipitation, humidity, everything it will be there as a column matrix at the C. Okay, so here I will be giving the initial conditions, that is in the form of temperature, as a, if it is 10 lakh nodes, 10 lakh by 1 matrix. Okay, and I'm sorry, 10 lakh by 1 vector. Okay, so here also I will be having a 10 lakh by 1 vector. So this will be the answer. Theta n plus 1 is, that is the temperature distribution in the next times. That is the answer. Okay, so I told that this is a time marching problem. So that will be the answer. So balance everything, you put it on the other side, and you are trying to get what is the temperature distribution. Okay, so if you can have the temperature distribution. Okay, so you can have the temperature distribution in the building model. Also, you can have the include the plant also. So that means you can include the air conditioning system also. So in our last class, I told that just whatever the heat load you are getting divided by 3, you will get what is the work input to the system. So that is a simple simulation. If you want a comprehensive simulation, even the air conditioning components also you can create nodes. For example, duct, airflow, everything you can create in the form of nodes. For that also you can find out what is the temperature distribution. So that is possible, that is available. Okay, so that is called HVAC calculations. So now it is being done. Okay. Okay, so what is the application of building simulation software? It is useful for heating and cooling and calculation, or sizing the heating and cooling equipments. While cooling calculations are transient, heating calculations are steady state. You can calculate the building energy consumption for a year or for a month. Okay, case may be. You can do the HVAC plant analysis. Now it is available. You can do the CFD analysis. You can go for daylighting model also. So you can find out, you can plan for daylighting. Okay, for a particular, you can do it for year round, so that lighting is available. For us and all, it is not a problem. Year round we will be having lighting, but where the countries which are located beyond 40° north latitude, so you know that day's length will be smaller for most of the time. So that time light is required, even the solar energy is required. So doing the daylighting simulation will be useful for them. Okay. The next is you can do the visualization of a site layout and the solar lighting. So that is also possible. That means even sun path diagram like that, you can have a lot of data from your building simulation solver. Okay. And these are all the general blocks. We are going to discuss about these general blocks. Okay, so we will have a detailed discussion in our subsequent sections. So we will be having layout where we will be drawing the drawing of the building, and you will be mentioning all the activities inside. What are all the activities you can mention? Okay, so construction details. Okay, so what are all the different type of constructions? So whether it is fully exposed, partially exposed, okay, whether it is partial exposed ceiling or partial exposed floor. Okay, so all these things are possible. So these details you can give it in the construction details. So regarding openings also you can use, whether it is a vent, okay, whether it is a vent or opening, whether it is a glazing, whether it is a input airflow inlet. Okay, so you may be taking fresh air inside, so that also it will be called as opening. So all these details you can do. So even lighting studies you can do it, HVAC studies you can do it, CFD studies. This I told you already. And this is how the blocks will be. So you can do the heating design, cooling design, simulation, CFD, and daylighting. So all these things are possible. And what are all the library components you will be having? Okay, so today I think since time is not there, so we will have a quick go through of what will be having. Okay, and maybe tomorrow we can have a detailed discussion on these components. So you will be having constructions. Okay, so different library for construction. That means a variety of materials will be available. So all these libraries will be there. The solver itself it will be there. You need not worry. Just you have to pick the material and put it in the solver. Similarly for glazing materials. Okay, so you have to. There are also a lot of materials will be given. A lot of glazing materials will be given, and other materials. Okay, other construction materials. Okay, construction. This is construction type. Okay, so this is construction materials. You can have different pans, different textures, different window glasses. You can plan for local shading. Okay, window blinds, vents, schedules also. I told what are all the different type of schedules. Okay, so office schedule will be different, hotel schedule will be different, school schedule will be different, factory schedule will be different. So all these schedules also it is ready-made available. So just you have to pick and put it. That's it. Or you can edit it for your convenience. Even holidays also, it is worth mentioning holidays also. Okay, you during holidays your AC and other things will not be working. Okay, and you can give the profile, load profiles also we can give. Okay, so these are all the library components available in the building simulation software. And similarly, you can give the templates. So what are all the templates that is possible? You can give activity templates, construction templates, glazing templates. Okay, standard glazing templates, facade templates, HVAC templates. Okay, so what type templates means? Is it a window AC or if it is a split AC? Is it a ductable AC? So for that, a template will be there. Okay, ductable, central plant, chiller. So all these templates will be. So like that, for everything, a template will be there. Location template. Okay, so in what location it is there? Hourly weather data, pressure coefficients, metabolic rate, tracks. So all these things I think we have found in our heat load calculations. So legislative regions. So in which region we are doing the calculation? What are the corresponding energy codes? In India, the energy code will be different. In US, they will be following a different energy codes. Some will be very stringent and some will be lenient. So sectors and the world time zones, all these templates are available. If you go into the solver, all these templates are available. Okay, and what are the things? So standards we should know. So we should be having a dimensioning. So how to go for dimension? So if it is a block dimension, if they are telling it about a block, so this whatever they are shown in the blue color, so that is the block height. You should not take block taking the roof construction also. Okay, so you should not. You have to include the floor construction only. So there are some standards so that it can be compatible for discussions. Okay, so everywhere if you follow the standards, so that will be compatible for discussions. Or some you follow something and others following something, so that will be. So in energy solvers, that is the building simulation solvers, up to this only you have to take it. Okay, as a block dimension. So similarly for ground floor block dimension, you don't take this one roof. You don't take up to this one. You have to take. Similarly, there are, I told, different types of constructions. So what are the different types of constructions? So the block dimensions you can give it. Okay, so all the thick lines what we have. So those are all block dimensions. Zone surfaces. So if you call it as zone A, zone B, that is room A, room B. Up to this only you should call as a zone. Okay, up to this only you should call it as a zone. So that is a standard. Then only everyone will understand in the same pattern. Okay. Similarly, a zone air volume. So that means this whatever yellow color it is shown, that is the zone air volume. Okay, and what we call it as external wall construction. it should be exposed to solar. Here you can see it is exposed to solar. So that is called as external wall construction. Semi-exposed to wall construction. Okay, so this one, okay, it is a semi-exposed. It is not totally exposed to wall construction. Okay, it is a semi-exposed. Okay, and we have semi-exposed ceiling construction. Okay, so here you can see. So this is semi-exposed ceiling construction. Okay, I'm sorry. So this is semi-exposed ceiling construction, and semi-exposed to wall construction. So here you can see this is a semi-exposed wall construction. Okay, it is not exposed to solar radiation. Okay, so that is why it is not interior also. It is not like a partition like this. So that's why it's called a semi-exposed. And this is a flat roof construction. So this is flat roof, and you have pitched roof. This is pitched roof, sloped roof. So where you have rainy and a snowy place. Okay, so the rain and the snow it should not settle. For that you will be having pitched roof. Okay, and external floor. You have internal floor and external floor. So internal flooring, external floor is shown. Then internal partition construction. So this is internal partition. So this is exposed partition. Okay, exposed to wall construction. So that means we have some standards. Okay, so we have some standards, and when we are giving, okay, so you have to go and give. So when you are constructing a building, when you are doing the modeling, so you have to tell whether what type of roof. Okay, so there you will be having, maybe in the solver you can see whether it will ask whether it is an external wall or semi-exposed, or it is a flat roof construction, or whether it is pitched roof construction, whether it is a ground floor or in the inside floor or external floor. So all these details we have to give with the construction materials. Construction materials separate template will be there, but this also we have to give a template for what type of construction it is. That also we have to give. Okay. And these are the steps in building modeling analysis. We are going to discuss this in detail. So I'll go through this. Okay. So we'll go into a new site, new building. You first to draw the building, and you collect the climatic data, and you have to give that all the data. You have to size for heating and cooling. Okay. You have to size for heating and cooling. What will be the cooling equipment size, and what will be the heating equipment size, and you have to do it for. You can do the simulation also, year-round simulation also. You can do it for the hourly data and hourly results. Okay, so first you have to do it with short calculations. First you can go for heating and cooling design, and after that you can go for simulation. Even in simulation also you can go for just for 1 week, then one month, and then you can go for 1 year. Because there will be a problem when you are going for year-round simulation and all. You go for a very big building, so then it will take long time. So then it is a problem for it will take lot of time. In a small computer, you are doing it for a very big building. So then that means you have to go step by step. You can do it every month. You can mention the interval. You can do every week. You can give months, and you can do it for the 1 year. So depending on your computer capacity, you can go for full simulation. Okay. And so this is how you are going to have building model. And if you are going for cooling design, these are all the parameters you are going to get as output. Okay. So regarding this, we are going to discuss tomorrow in detail. So first, it is an introduction. Okay. So first introduction. So in a cooling design, so what are all the parameters we have? We have outdoor dry bulb temperature. Okay. So this is like it is all your systems are switching on. First, the location is Chennai. Okay. Location is Chennai. And calculation we are doing it for 15th July. I'll tell you why we are doing it for 15th July. Okay. So morning we are starting. Okay. Morning we are starting the air conditioner. Okay. So in Chennai means it will be air conditioning only. So morning we are starting the air conditioner. So this is the outside dry bulb temperature. So it is rising. And we have radiant temperature and operative temperature. So I think you would have heard these words, radiant temperature and operative temperature. So radiant temperature, it is the weighted average wall temperature based on the. So I told you, I think. So if you want, this is the thing we have discussed already. Mean radiant temperature, it is the cumulative of all the wall temperatures. Okay, with this shape factor. Okay, it is like a weighted average with the shape factor. So that's why you call it as mean radiant temperature, or you can consider as a mean wall temperature. Okay. And operative temperature also. So it is operative temperature is a combination of convection and radiation. Okay, there also we are weighted averaging. Okay, we are doing the weighted averaging based on the convection coefficient. Okay, so from this we understand that mean radiant and temperature it will be very much higher because it is the surface temperature of the wall, and operative temperature it will be between. Okay, it will be between the ambient temperature and the surrounding temperature. So that is how you will be getting the distribution. Okay, so here you can see that the distribution. So the radiant temperature is higher, nearest wall temperature, and operative temperature. Okay, so it will be between the air temperature and the radiant temperature. Okay, so it is weighted up. And what is happening to the air temperature? We are conditioning. We are doing the air conditioning. So cooling and humidification, air conditioning. So the temperature is reduced. Okay. And what about the loads? So we have various loads. Whatever the loads we have studied in our heat load calculation, all these loads are appearing. Glazing is there, sealing is there, through sealing how much is coming. So here you can see it is all these things are reduced. Floor, how much it is coming, ground floor it is coming, roof, external infiltration, okay, external vent, through that how much it is coming, lighting, how much it is there, computer equipment, and occupancy. So all these things will be there only during daytime. Internal gain and all it will be there only during daytime. Okay. So all these are loads. Out of that, the solar gain, the external windows, it is very much higher. You can see that solar gain, it is very much higher. Okay. So this is morning. So maybe morning, and again west. Maybe it is east and west. There is a glass exposure. So that's why I'm having it like this: east and west. And these are all the loads. This is the rate of heat entry into the building, rate of heat gain into the building. Okay. To overcome that, I have to supply cold. So that is given by this blue color, zone sensible cooling. Okay, zone sensible cooling, it is given by the blue color. So these are all the rate of heat entering into the building. So this is the rate at which I am removing the heat. If I remove the heat at this rate, I can maintain this temperature inside the room. Okay. So this is a type of control. It is possible only in proportional controllers. If you are going for on-off controllers, so it is very difficult to have a control like this. On-off controller, it may not go like this. Okay, so it will go rise and fall, rise and fall. So that is how it will go. Okay, here also that variation spikes will be there in the temperature. Here it is assumed that pro rata or proportional to the load, we are supplying the cold. Using, for example, you think there is a AHU with a proportional controller. So that will be supplying like this. Okay. Okay, so our sensible cooling is like this, our latent cooling. Okay, so total cooling is given like this. The difference between these two, it will be latent cooling. So that is understood. If you shade this, that is latent cooling. Because if this is sensible and this is latent, this is total, the difference is latent. Okay, when the latent will be more. So already I told you. So a comprehensive cooling design simulation. Okay, so how we will doing cooling and heating design, that we will be, discuss tomorrow. Okay, and how to do the heating design. So I told heating design is a steady state, no transients. So that means what you will be having blocks like this one. Okay, so what is happening? You are finding that the air temperature is always, and the radiant temperature is always, and the operating temperature is always, the outright temperature is always. So for Chennai, you are finding that the minimum temperature is near 19. That maybe at December night time you will be getting. So that's it. That is the lowest temperature. Okay. And for that, if I calculate a heater, so it comes only for 4.35. So you see the building model. You can see it's a very big model. This much big building. So you are getting only 4 kilowatt. Okay. So that is logical. That is logical. You know, for Chennai, I told already heating is not required. The heating is not required. So in that heating thing also, what are all the, so you are given glazing. Through glazing it is lost, and what's electrical and other things it is lost, and the most important thing, external infiltration. So what is glazing? Glazing means through the glass. Okay, so the heat is lost through the glass. So that's what we have to understand. So east west is there. So heat is lost through the glass. So that is possible. And external infiltration, because of that also we are having. And both added together, I am getting the zone sensitive heating, for which the value is coming 4.3. So here there is no variation with the time under. Okay, so if you want to go to heating, this calculation has been calculated at night at the maximum rate of heat loss. So for compensating that, it is 4.35 only. Okay, so it is okay, correct, logical only. Okay, so next is you go for year-round simulation. Okay, so when I go for year-round simulation, so the data should be there. Year-round data should be there. So year-round data is, you should have a year-round data for outside dry bulb temperature, outside dew point temperature, and similarly wind speed, wind direction, solar altitude, and solar azimuth. I think it is not that yet. It is wind direction only. It is there, and atmospheric pressure. Okay, and direct radiation and diffuse radiation. So direct radiation and diffuse radiations also it is given. And you can see direct radiations and diffuse radiation is more during May, June, July. July it is maximum. So that is why the heat load calculation it is made for July. So, okay, so radiation level it is higher. You can see December and all it is lesser. December is lesser. January, February it is lesser. So during July, June, July, so we have a peak. Okay, so that is why we are doing the calculation on July 15th. So somebody asked when I have to do that load calculation. So you have to see the yearly pattern when it is higher. So now you get a clear picture. Still you go for energy calculation, you will have a, so this is the output. This is external excitation for a year. Okay, so this is the response of the building simulation software for a year. So something interesting are there to note in this one. We will have a quick go through of what are all these interesting things we have to know. So this each spike it is shown here, it is for a week, and there is a drop between the spikes. So that is weekend, Saturday, Sunday. So because of schedule, okay, so you are having a gap there, and every first day of the week you are having a peak. Why? Because 2 days the heat will be stored in the building. Okay, and when you are starting the building, the first day on Monday you will be having maximum energy. So that is why you are having a peak here. And after you can see when it goes to the Friday, up to Friday it is dropping. So this pattern is common in all the things. Okay, so that is interesting. You can see that it is very interesting. This pattern is common. So every Monday the consumption, energy consumption, AC energy consumption, it is higher. Okay, and it decreases up to Friday. Then after that 2 days it is leave. Okay, so that means it is not working. Okay, it is because of the schedule. So that's why I say schedule is important. And after that, what is happening to the air temperature, radiant temperature? Okay, so every day the radiant temperature, okay, the operative temperature, okay, and the air temperature. So it is for every day it is given. Okay, and outside air dry bulb temperature. So that is also given. Outside air dry bulb temperature, it is also given. So if you want to have a clear picture, you have to go into that, like what we have seen now. So for July 15th, we have seen a clear case. Okay, so I think that is sufficient. Okay, and what is the distribution for a year? What is the distribution of the various loads? So we find the same pattern for various loads. Okay, we find the same patterns for various loads. Here you can see solar gain external windows. So that is higher in the beginning of the year. So that is January, February it is higher, and again at December, November, December it is higher. It is because of the solar orientation. So year wise, I mean month wise, the sun is moving in the north south. So that means during the south, that is November, December, and January, February. So the sun will be at the south. Okay, so that means the sun sun will be at the south. Yeah, sun will be in the south. So that is why we are having a lot of radiation. So that means in the south we are having a glass, okay, south or southwest. And here you can see in this area we don't have the exposure. So these things you can small things you can see, and you can decide how much will be the and here these are all the cooling loads. So the pattern is same, and except whenever the load is higher, so we have the different patterns, okay. And we have something interesting here also, okay. So here you are finding because of exposure during January and February and December also, okay. So we are having a higher loads, okay, and that also we are able to see. And here you can see how you can correct this. You can change the orientation of the glass, okay. So that you can correct this, okay. And what is happening to the mechanical ventilation, mechanical and natural ventilation? Natural mechanical ventilation will work whenever the outdoor ambient air is smaller. I mean, temperature is smaller. Ambient temperature is comfortable. Okay, so that time it will take the air from outside. Okay, so here you can see when it will be comfortable. Only October, November, December for Chennai. January, February, March, it will be comfortable. At that point, it is taking air from outside. Okay, mechanical ventilation system. Okay, so it is taking air from outside. So that means what it will just see when ambient temperature is less. At that point, it will pump the air inside to the building. So at that using that, you can conserve the energy inside the building. So only if you install that, this will work. Okay, so it has been enabled in the solver. So that is why this component is appearing. So all sorts of this, okay, so you can present it in graphical form. You can get it in tabular form also. So that we will discuss tomorrow. So all these things, details, it is possible for us to study in a building energy simulation software. Okay. So I think this is sufficient as the introduction for building energy simulation software. We will continue our discussion on heating and cooling of building tomorrow. Okay. I have completed my discussion. So if there is any query, any question is there, I think we can have a discussion. Okay. So any question is there?
Yes, sir.
Yeah.
In wall calculation, U value can be more than 2.
Involve?
In wall calculation, U value can be more than 2. Adinor question get
2, what is the unit?
Let's say 2 to question mark.
Answer for the unit. Okay. Yeah, so you can have it. It depends on the regulation. Okay, it depends on the codes. Okay, 2 is lower only. Thank you. You can have it. Okay. Yeah. Next.
How about ISVE software? IESVE software. Are we discussing about in this workshop?
No, I'm not discussing about any specific. So most of the things I'm taking from a design builder, and I'm discussing. Okay, so I'm not very specifically mentioning about any software. Okay, so I should not do that. Most of my discussion I'm doing it in general only. Okay, so you can mention, you can give your thing. Okay, so details I will check it out. Okay, how it is worked. Okay, yeah. So there is a question in the chat.
How can we reduce Monday peak values?
How can we?
How can we reduce Monday peak values?
Monday peak values. Yeah, Monday peak values. I think you can ventilate nighttime. You can do the ventilation. Okay, that should be an automatic night ventilation, because you are finding night times temperatures. If they are lesser, you can do nighttime ventilation so that building inside temperature can go down. Okay, and the thing is your air conditioner will be working for a long time. So that is why the energy consumption is more at that point of time. Okay, your air conditioner, it will be working for a long time without cutting. Okay, so that's why the energy consumption will be more. But if you go to day 2, so that is because all the residual heat has been removed. So continuously, it will maintain a low temperature. So that will be sensitive to external solar radiation only. Okay, But at Friday night, you are closing the office, and Monday when you are coming back, all the, since you are not air conditioning, all the building components, okay, namely walls and other things. So it is a heavy mass, okay, mass into specific heat of that system, it will be very much higher. So that means if you want to pull down such a huge mass, okay, huge mass and specific heat, that is heat capacity, down to the temperature. So that means you have to work your compressor of your air conditioning system. It has to work for a very long time. So then only you can do that. Okay.
Sir, and the U value can be less than 2 watt per meter square degree.
Yeah, it can be. It is a lower value only. So you have to see the case. Okay. So just now, just like that, I cannot say. It is a okay. So 2 is a agreeable value only. Okay. Yeah. Due to external zoning, how much distance we need to keep from the perimeter of external surface of the building. Okay. The distance, okay, so from the perimeter of the building, so you can do the simulation, okay, you can do the simulation, and you can find out. See, all these things, it is possible to simulate. You can change the distance, and you can so by rule of thumb we cannot say, okay, so you could do the simulation, okay, and you can find out, okay, so how much may be the distance from the perimeter. And it all depends, okay, so it all depends on how much radiation it is coming. Okay, so since the solver is there, you can go for simulation and you can find out what will be the best distance. Okay, so you can do that, no, so you can have it first, you can have it for 10 feet, and after that you can go for 15 feet, and you can do it for 5 feet, and you can see how much will be the. So that means just like that, giving some suggestion, thumb rules. So I think it is better to go for simulation and then find out. Okay. Yeah, so it should be optimum. It should not be very much lower, or it should not be very much higher also. Okay. So can you elaborate RH fall and rise in the graph that you displayed? Okay, I'll just one. Yeah, so here you can see this is the RH graph. Okay. So this is the relative humidity graph. So what is happening in the morning? Okay, when you are maintaining the condition, okay, so in the morning, I think you are maintaining your AC, if it is running, so you will be maintaining the condition. So naturally you will be having whatever you have designed, okay, so 40% or 45%, whatever that will be there. Okay, so nighttime, you'll be having general condensation will be there. Okay, general condensation will be there. So what will be happening is because of condensation, so in the atmosphere, okay, or from the building, so the water droplets, it will be settling on the surface of the, for example, car is there, any equipment is there, okay, car or anything is there. So because of that, the general ambient, okay, so ambient temperature in the relative humidity of the ambient will go down because moisture is separated. Or in simple place, you can understand like dew point temperature. During night time, the temperature of the surfaces, such as metallic surfaces, okay, like car body, car glass, and also the temperature will go down below the dew point temperature. So that is why from the atmosphere, the humidity will be settling on the surface of the this cold surfaces. So because of that, the moisture will get separated. So that means the air will become dry. So this is a natural trend. So usually it will be happening. So even in winter it will be very predominant. You can very well understand. So during night times, you can see the condensation at the grass, dew, and everywhere around. So the moisture in the air, it has separated, and it has settled on this surfaces. So what will happen to the air? So air will become deprived of the moisture. So that means you will be having a lesser relative humidity. So that means it can hold more moisture, but now the moisture has got separated. Okay, so the RH will be higher. I'm sorry, RH will be lower. So that is how you will be having. So early morning, okay, so early morning and night times you will be having a lesser RH. So this you can see it in climatic data also. So if you take the climatic data at night times, you find your RH will be coming down. Okay. So during daytime, the RH will be increasing for a coastal climate like Chennai. Okay. So hope I have explained you. So anything is there? Okay. One. Wait. So yeah. So yeah. So some expert he has given suggestion. Okay. Night flushing is the best solution for reducing the loss. Yeah. I think that is what I told. Okay. So any other question is there? Yeah. Okay. If there is no other question, thank you everyone for joining. Okay. So tomorrow we will have a discussion on cooling and heating designs. Okay. Using energy simulation software. Thank you everyone. Thank you for joining. Oh, is it a question? Is a best solution for reducing load? Is it practically implemented in commercial building? What is the percentage of load reduction achievable if we follow this night flushing? So it depends on the temperature. It is very simple. So night flushing, if the surrounding temperature is very less, yeah, a smaller percentage is okay for reducing the load. If a surrounding temperature is little bit higher, so then you require a larger amount of air to bring down the building temperature. So it depends on the temperature. Okay, so the percentage of air to be circulated, so it depends on the ambient temperature. Okay. Yeah. So I thought that it was an explanation. So now only I found that it is a question. Hope that explains. Yeah. Thank you everyone. Thank you for joining.